There we go. All right.
They're gonna getting a poker face by Lady Gaga.
Oh.
Because I'm currently in the process of trying to deal this figure.
Yeah.
They're our fans. No, they are. I just need stuff to cover it. Yeah. Because I try to like put it on air that
Yeah.
So I'm just like, I'm just gonna cover it, it feels better.
Yeah. I understand that.
Let's not make it too long. And I think my older yeah, my
All right, we're gonna get started here in a second, folks. Let's get signed in. Yeah. Oh, yeah, that's pretty cool. The spring trap is usually creepy. Like, you know the lore too.
Yeah, you know the lore about it being literally a man.
Yeah.
But like, it's cool when I go to school, like, I made a joke with my mom, like, you're the finance of Freddy's tattoo, and she's like, please don't. Stop it, me.
I do whatever I want, man. I don't even care what I think about it.
What if I want to get spring trapped in my booty cheek? That's my business.
Yeah, right. Let's go ahead and get started, folks. We need to get going. So if you're not signed in, please hurry up and do that. And for some reason, it does this thing where it kicks people out. Don't we love it? All right, ready to get started. All right, what is the function of lysozyme? All righty, so lysozyme, it is an enzyme that is made by your cells. It's found in your saliva and in your tears and in some other places in the body. And what it does is it breaks down peptidoglycan. And it's part of your innate response, part of the chemical responses. So which of the following is not a granulocyte? Alrighty, so all the phils are the granulocytes. Neutrophils, basophils, and eosinophils. There's one other granulocyte that we learned about, that's the mast cells. So it's the add-on to that. And then our agranulocytes, remember, will be our monocytes, the cells that are derived from the monocytes, which are, if you guys remember which ones, macrophages and dendritic cells, right? And then also the agranulocytes include the lymphocytes. And there's two lymphocytes as well, the B cells and the T cells. So that's that. Moving on. in the inflammatory response, what is dolor? There's rubor, calor, tumor, and dolor. They each represent one of these, and which one is dolor? All right, so dolor is pain, rubor is the redness, the swelling is tumor, and the warmth is calor. All right, a pyrogen. Now we're getting into stuff we haven't gotten onto in the lecture in class yet. Does anybody want to guess what a pyrogen is?
Infect fevers.
Pyro, yeah. I feel like this word kind of goes hand in hand with what actually happens. Thankfully.
Hot.
Yeah,
Hot.
like fire, like you think like a pyromaniac is into fire, and then I think heat, and then that's right, it's gonna be fever. Good one. All righty, next question. All right, fever is really just useless and it might even be harmful. Is that true or false?
Very.
So we're going to talk a little bit about it today. All right, so this one's false. Fever has a purpose. And so we're going to talk about that a little bit today in a little more detail. There's a reason why you get fevers. It actually serves a purpose in fighting the infection. So what is the general purpose of the inflammatory response? Why do we have the inflammatory response? So the real purpose of the inflammatory response in your body is to get somebody there fighting something somehow right off the bat. So that's the whole point of the inflammatory response in the innate immune response. The whole point is to get the first defenders there. Your neutrophils especially, because they're usually the first guys on the scene. They're going to come in there and say, you are bad or you are self. And that's going to destroy anything that's not self and just start eating it up and pooping out all of the waste products after that. So that's pretty much what the whole point is just get that going and then start gathering all of the info that you need to get your next phase in. So interferon, we didn't get to this. What do you think it's going to be? It's okay, just make a guess because we're going to talk about it at the end of chapter 15. Right, so interferon is a molecule, it's one of your cytokines, your signaling molecules. And what it does is it basically signals the neighboring cells that you're infected so that the neighboring cells can get ready and prepare to prevent viral infection from spreading too far. I think of it as like the call to your neighbor, like basically saying, hey, I'm getting invaded, somebody's breaking into my house. And they're calling the neighbor saying, he's in my house, I don't have a lot of time left, but at least you can get your shotgun ready. And then the neighbor can have the shotgun ready. So it's sort of like that. It's for viral infections. All right, next question. What is diapedesis? I misspelled it, but that's all right. Dia, it's supposed to be D-I-A.
I wouldn't know.
P-E. Diapedesis. Yeah, so diapedesis is whenever your white blood cells that are in your bloodstream are going to move into the tissues. And the way they do that is by squeezing in between the cells of your capillaries. They literally like just squeeze between the junctions of the cells to move in there. And that process is called diapedesis. All righty, question 9. Which of these is not one of the 3 types of the complement pathway? Again, we haven't gotten to it yet. Make a guess. We'll talk about the 3 ways that complement can get activated. Complement pathway is part of your innate response. And it can get activated in 3 ways. The classical pathway, the lectin pathway, and the alternative pathway. Those are the names of the pathways. As it turns out, the alternative pathway can be activated by peptidoglycan. It's just not called the peptidoglycan pathway because it can be other molecules besides peptidoglycan. It just falls in that category. So, all righty, next. Which of these is not one of the effects of the complement pathway activation? So we're going to activate the complement pathway. We're going to talk about what it does. What is the purpose of it going to be? So it has three major effects. Once you activate your complement pathway, one of those three ways, you can have these three outcomes. One of these is not like the others. So this is memory. Memory is only going to come with our acquired immune response. That's the chapter 16 stuff. You never get memory from any of your innate responses. So your innate responses are just able to see self or non-self and then attack based on that engagement, but they won't have memory that will be specific to that thing that they saw. So that's what your adaptive response is going to be for. And that's what we're going to get into with chapter 16 when we start that today. Whew, it's warm in here and I had to wear like this sweater dress thing and a scarf, but I don't want to take it off because I think it's cute. My back is killing me, man, because I'm old. All right, great job, guys. We did really well considering some of the questions we haven't gotten to yet. All righty. So let's do it. So let's finish up with chapter 15. We left off last time getting into our inflammatory response. Let's see where we were. We mentioned briefly the phagocytosis stuff, so I'm going to start here to kind of reprise into this stuff. So phagocytosis, which we've talked about since pretty much the beginning of the class, phagocytosis is phago-eating cytosis by the cell. So cells coming up and eating other things. So that could be dead cells, debris in an area, or invading bacteria or viruses or anything like that. So anything that is waste or foreign, that's when phagocytosis is going to occur. And it's done by our white blood cells. So this can be done by your granulocytes or your agranulocytes. It just depends on what cell we're talking about. The process of phagocytosis happens with these steps. First is chemotaxis. Chemotaxis means there's a chemical signal released in response to your injury or infection. Basically, the cells in the area are crying out for help. And so they're releasing signals, and they're going to be in the form of different chemicals asking for help. And then your phagocytes, your neutrophils and your macrophages and your monocytes are going to hear those signals and migrate towards them. So they're going to follow those signals and move to your area of infection or injury. That response to those chemical signals, that's chemotaxis. Then we have ingestion. Once your white blood cells get to that area, they're going to come and interact with molecules in the area, basically. So they will interact with these molecules and either recognize them as self or not. And if it's not self, then there's specific things, which remember we called last time, I know it's been a while, but PAMPs. Remember pathogen-associated molecular patterns? So things like peptidoglycan, LPS, or double-stranded RNA can automatically signal our innate response to ingest things. And so when we recognize a PAMP, which is just a generic marker of a bad guy, we recognize a PAMP, then that'll be using markers on the surface of their cells, basically lock and key interaction, right? Their lock and key interaction with something they're finding in the area. Let's say I'm a phagocyte and I come and I interact with this and I say, oh, this is definitely not a self thing. So I know it's not self, so I'm going to eat it up. And it is that basic for the innate response, all right? So that's the ingestion step. And so we know that what it's going to do is say, recognize it, usually by the PAMP, and then ingest it up into something called a phagosome. Zome is just another way of saying a vesicle. So a phagosome is the vesicle that you put it in when you eat it, all right? We have other vesicles that exist in our phagocytes, our white blood cells. Those vesicles are called lysosomes. And so we kind of already know a little bit about them. But a lysosome is a vesicle that contains things like lysozyme, go figure, which breaks down peptidoglycan, as well as other like toxic molecules like our oxygen-based free radicals, acids, all sorts of toxic molecules that we just store in lysosomes. Now, phagosomes will merge the lysosome with the phagosome that we ate up the bad guy in and merge those things together. and then start digesting it. The formation of those merged vesicles is then the phagolysosome. So we form the phagolysosome, and then that will end up destroying whatever it was that we have in that phagolysosome when we merge that lysosome in and emptied its contents in with whatever was foreign or waste or whatever it was. All right, so we'll destroy it, and then we usually excrete it. This is especially true for our neutrophils. These guys will just go in and say, oh, you're not self, eat it up, and then, poop out all the parts everywhere into its environment, and then just leave it there. They don't do anything else with it. They just go and eat things up, digest it, and poop it out, which might not mean a whole lot to you right now, but it's going to be important later on. We start talking about how you get your actual memory response and your adaptive immune response. So we recognize our PAMPs, our pathogen-associated molecular patterns. This can include things like we've already mentioned, peptidoglycan, lipopolysaccharide, which is endotoxin, or double-stranded RNA. Those are just big examples. We can automatically see that as foreign, eat it up, and then merge it with our lysosome that has our toxic compounds in it. Most bacteria can kill most bacteria can be killed or other foreign things broken down within 30 minutes of that phagolysosome formation. All right, so that is phagocytosis. Now moving back into the overall inflammatory response, we already talked about these, but I'm just retouching on it to remind you guys, rubor, calor, tumor, and dolor are major signs of our inflammatory response happening. So these are macro signs that we associate with inflammation. Rubor is redness because we have increased blood flow to the area. So blood is red, that's why it turns red. Calor is warmth. We increase the heat to the area. Part of this is because blood is flowing into those areas. The other part of it is the heat response itself, which we're going to talk about when we get into the fever stuff here in just a minute, what the benefit is of warmth. Tumor, which is swelling. So when we think of tumor as growth of cells, but in this case, tumor is just the Latin term referring to a swelling. So this is from fluid moving out of the bloodstream and into the area of injury or infection. Remember, the reason that we have that going on is because we have the chemical signals, we have nutrients to help the cells that are fighting in the area, and we have the cells that are doing the fighting in the area, all moving in there with that fluid out of the bloodstream. And then we have dolor, which is pain. This is usually because we have the stimulation of those nerves due to the injury or perhaps even the infection. And then we trigger that pain response. Even if you have an infection, you sometimes will feel pain, right? And so the whole reason we're having that pain response is just so that your body knows that something's off. And so it helps send that signal to the rest of your body, letting you know about that. So part of that can be that too. You can also sometimes have loss of function. If you were like me, man, you've got my freaking sciatica or whatever it is that makes my back hurt, I definitely have loss of function in my ability for my back to function or whatever associated with the inflammation from probably ruptured disc or something like that in the spine, which is the case for 90% of sciatica cases, by the way. So anyways, so that sort of stuff from that inflammatory response can also be a sign of the inflammatory response, not being able to have function in whatever area. All right, so chronic inflammation, obviously, if you have this constant movement of these like neutrophils trying to destroy things and get rid of, all the stuff and all these signals calling for get rid of as much as you can in this area that isn't needed, that can lead to progressive effect of damage in the area as well. And because we have this heightened sense of constant panic, if you will, from your innate response, that panic can kind of incite improper immune responses as well. So we constantly have signal of fight, 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 fight. And then that can lead to triggering improper immune responses and lead to things like autoimmune disease, all that sort of stuff. Damage of tissues, autoimmune disease, and all this can happen from chronic inflammation. So some of the points, some of the purposes, more specifically, of our inflammatory response. We want to attract immune components to the area. We want to set in motion repair, and we want to destroy microbes and block further invasion. So we can increase blood flow to an area and decrease blood flow from an area. So we can get the cells to the area, but then decrease it out of the area because we don't want any open blood vessels bringing potential microbes in directly through the bloodstream. And so we can control that sort of response, and that's part of the reason why you'll have that swelling involved as well. All right, so here are our major events just to walk us through pictorially in what is happening. Let's say you step on a nail here in step number 1. You step on a nail, we introduce bacteria into the wound, and then we have cells that are just naturally in the area, things like mast cells or even the cells themselves that have been injured, like your skin cells and things like that, will release chemicals saying, help, I've been injured, or the mast cells can just automatically, because they are already in the tissue, already waiting there, can start releasing histamines and things like that that are inciting the inflammatory response immediately. So those guys are already there where the injury has happened. But we're releasing some chemicals that are going to allow us to increase blood flow to the area and prevent blood flow out. So controlling vasoconstriction and vasodilation in response to what's going to happen next. So we're releasing our chemical mediators, and now we've called in neutrophils. Our mast cells and our damaged cells in the area have released chemicals, and chemotaxis has allowed our phagocytes to start moving in, right? So our phagocytes in this case are first line defenders, your neutrophils. 55% of your white blood cell count is neutrophils alone. They are number one, your primary protector in your innate response, right? So your neutrophils are moving into the area because they got signals from the mast cells and from the injured cells. They're coming in there, and they're going to start in with phagocytosis. When they move in, plasma, your liquid portion of your blood, also moves in, right? And that's what's going to be happening next. So now we're eating everything up. We have edema, swelling, because of all that fluid that comes in with the cells and the signals and everything like that. So that's edema. And then pus. Pus is almost entirely neutrophils. You didn't know that. It'll be neutrophils and some bacteria, but it's primarily neutrophils. It's actually your white blood cells that you're seeing when you see pus. And so when you have this sort of infection, we're walling off this infection by controlling the blood flow to the area. We're bringing in these white blood cells, and they're sort of trying to wall everything off and control and keep this infection and introduction of foreign material completely local. And so our neutrophils are going to do that by eating everything up. And so here goes our neutrophils. They're eating up anything that's not self, and they're pooping out all the waste from eating them up. So they say, oh, you're not self. They break it up inside. Remember, 30 minutes to break down the bacteria, and then just poop out all the little parts of the bacteria in the area around them. All right, so that's what's happening there. Then finally, after all this is going on, and we start bringing in healing things, so we can start our healing, and that might lead to a scar, because your body doesn't care how pretty you look. Only you do in your brain. So your body is just trying to heal up and seal up the wound, and so that's where we might get scars forming. And now that our immune system response is going on, we finally brought in macrophages. So remember, a macrophage is just a monocyte. Monocytes are in the bloodstream. And once the monocytes move out of the bloodstream into a tissue, they differentiate into macrophages or dendritic cells. All right. So now we have had all of our neutrophil response going on, and now we're bringing in the macrophages. They have to be signaled out of the bloodstream and then differentiate into the macrophages. So it's a little bit delayed response compared to the neutrophils. So they come in second. But I got to tell you, those neutrophils are important for that first line of immediate destruction. But if you didn't have your macrophages, you would just be constantly getting infections. You have no memory whatsoever. Macrophages, yes. Macrophages are not memory cells, but they are the go-between. So the macrophages are going to come and pick up all the waste that the neutrophils left behind. They're going to pick it up and discard it. So they're like, I don't want to say they're not the garbage collectors. That's not true. They're like the investigator where maybe we have the war going on and we know we're fighting enemies, but we don't really know what's going on. So these are the guys that are coming in there and say, okay, now we got to figure out what's going on. Now we got to be more specific about how we're going to fight this fight and start bringing in the big guys. And we need to know if we need to bring in the big guys as well. So the macrophages are going to control that response. So your innate response, just destroy it if it's foreign. That's great. That's your neutrophils. But now our next phagocytes, our macrophages, they're going to pick up the waste from the neutrophils and help your body decide, do we need to call the bombers and the specialists then? Or is this okay how it is? And they're going to take all of that stuff with them that the neutrophils left behind and bring it to your next step, your B cells and your T cells, through your lymph nodes. Bring it to those cells and say, do you guys want to do something about this or not? And if they get enough signals back and forth, we'll control the next step in the adaptive response. So if it weren't for the macrophages to come clean up the mess that the neutrophils left behind, as well as start that next step into activating the adaptive response, we wouldn't be able to have an adaptive response without those macrophages. So macrophages come in, And we can start healing then. A lot of times you don't always need to rely on your adaptive response to come and fix everything. But when you have some true pathogens, they usually have something in place that allows them to evade that innate response. And so that's where the problem starts to occur. When you have true pathogens being introduced into your body, they can usually survive that innate onslaught. When you go outside and you step on a nail and just some dirt gets in your foot and it's not a true pathogen, it's just environmental bacteria, and they're not really up for trying to survive all that BS going on with your immune system anyway, then usually your innate response will be able to get rid of them. But you introduce something like Clostridium tetani that gets deep enough in there, and it's got mechanisms in place to help it survive this initial onslaught. So now you have to rely on another step to help you through the rest of it. All right. So in the inflammatory response, we will have, increased blood flow as well as decreased blood flow, depending on what's happening in what stage in the injury. We don't need to worry about those steps yet in this class. But you'll have increased or decreased blood flow. We'll have chemical mediators called cytokines helping direct which cells come there and how they react. We'll call in our blood cells, like our white blood cells, our platelets that are going to be involved in creating the scab and helping with clotting and things like that to stop bleeding when we have damaged blood vessels and things like that. So all that's going to be mediated by the inflammatory events. So when we have edema and we have flowing in of the fluid and the cells from your bloodstream, it's not your blood that's bringing all of this in, right? It's the fluid from the blood bringing in your white blood cells. The only time that you have bleeding is if you actually injured like a blood vessel. So if your blood vessel hasn't ruptured, there shouldn't be blood going into that area. But if the blood vessel is ruptured, then we need to control the bleeding, and we also need to still be bringing in things from the fluid from your blood through the plasma, as well as your white blood cells that are in all of the signaling molecules, all of the nutrients and everything that's going to help drive the inflammatory response. So that fluid movement out of the bloodstream and into the tissue, that's where we get edema, that's the swelling. And that fluid, we call it exudate. So whenever we have blood components like plasma and white blood cells moving into the tissues from the bloodstream, that's called exudate. And that buildup of the exudate leading to swelling, that's edema, right? So the way that our white blood cells, which we mentioned previously, move out of our bloodstream and into the tissues, they're cells. So they don't just like diffuse through, right? So they have to squeeze between the actual walls of your capillaries. And so your capillaries are thin enough, they're usually only about 1 cell thick. And so they'll just squeeze in between the cells. They'll just like squeeze through that little space, that junction between. And that process is called diapedesis. So that's what that is. You can see it here, kind of squeezing through between, right here we got this neutrophil squeezing between the 2 cells of the capillary to move out of the bloodstream and into the tissues. Diapedesis. That's all driven by chemotaxis. Chemotaxis is telling them where to go and where to squeeze through and what tissue compartment to move to. And they move with the fluid, that's the exudate, and then that swelling that results is the edema. The whole point of moving that fluid in there is to bring nutrients, the signaling molecules, as well as to dilute toxic substances that are introduced into the area. And some of the chemicals that come in with the fluid are going to be involved in clotting. So they're clotting molecules like fibrin, and then your platelets aren't really cells. If you didn't know that, they're like parts of cells. Like you take a cell and you break off parts of it, and that's really what your platelets are. But they're involved in the clotting and creating the clots as well as the scabs to help with that healing process. And all of that comes in with the fluid as well. So it's not just fluid and then your white blood cells like your neutrophils, but things like platelets, things like fibrin, things like just the fluid diluting the toxins. All of that's important for your innate response. If you have, so as this inflammation goes on, later on, we will attract the monocytes, which will turn into the macrophages or dendritic cells, as well as lymphocytes will get eventually signaled to come into the area, usually by macrophages. So then the B cells and the T cells can start doing their job. We'll learn about their job in the next chapter in a little bit. But all of this is going to be driven by there still being an inflammatory response going on. If we had signals from the body, let's say you stubbed your toe, and we start sending out signals of like, help, help, something's going wrong, we need help. And and let's say the neutrophils just took care of everything, and the macrophages might not have a whole lot to do other than just clean up. Then you might not have a very strong adaptive response needed after that. But if the neutrophils can't control the situation, then the macrophages, that's when they're really going to be able to play their part in calling in the adaptive response. The adaptive response is essential for creating memory. It's when we get the adaptive response, the chapter 16 stuff, that we're going to be able to create our memory against something. And so once they see something, they can literally set aside memory cells. And once they've been activated once, it's super easy just to repopulate and have that response be almost immediate. It's why whenever you've been vaccinated for the measles and you walk by somebody that has measles, that you would never even have any symptoms or know that your body had actually been invaded by a measles virus. And I guarantee you, it might not have been measles, but probably something else you've been vaccinated against that your body has probably seen and has fought off so quickly that you never even knew that it actually got in your body. It just couldn't establish an infection because your adaptive response already got triggered and had somebody waiting at the door to take care of them. It's really quick and really important for the memory stuff there. All right, so that's what your B cells and T cells are going to do, and that's in the adaptive stuff. So moving on with inflammation, we already know about rubor, tumor, calor, and dolor. So part of calor leads in with the fever stuff, so the heat part of it. So what fever is when you have an elevated body temperature. So we can actually do this locally when you have warmth in an area where there's an injury. We can kind of control the temperature locally by increasing the blood flow as well as signaling there just for increasing the blood, the temperature there. But you can do it universally as well, so systemically. And this is almost always a sign of infection when you have this systemic body temperature rising. So if you have a fever, we're almost always going to assume there's an infection going on somewhere in your body. You can sometimes see fever happening when you have abnormal response from your body to something, but that's usually a sign of something else like cancer or allergies. Your immune system is still getting activated somehow. It's just a matter of why that might be happening, but it's very commonly associated with infection. And if you have an infection, you almost always have fever or at least localized increase of temperature. So we have the low grade, moderate, and high grade fevers. Low grade is anything from 100 to 101. If it reaches 102 to 103, then we're at the mid range, and then high is anything over 104. If you're having a high grade fever, you need to go into the ER. So once we get to about 105, that's a temperature at which your own proteins inside of your cells will start to denature. And that's where we start seeing dementia and people having seizures and things like that. Is because literally the proteins in their brain are getting denatured and they're not able to function properly. And so that can be irreversible, and damage from a high grade fever can be permanent if you didn't know that. And so some people don't know that. And so I had a friend of mine at OBI, she was one of my supervisors when I was a phlebotomist, and her daughter had permanent brain damage and has learning disabilities and things like that associated with having had a high grade fever that she was trying to manage at home. She didn't know that it was so high that she should take her to the ER. She just didn't know. Nobody educated her on it. Her temperature was about like 105.6 or something like that. And so she's alive, the daughter's alive, but she had brain damage issues related to having had a high fever. So definitely don't let it get too high. If it gets to 104, that's the time to be worried.
It also just hurts.
Yes, yeah. All right, so pyrogens are chemicals that can incite fever. These can either be endogenous or exogenous. So if it's endogenous, that means that your body is sending signals to start the fever. So this could just be like, hey, I saw something foreign, let's make signals to start a fever. But certain foreign things can just automatically start a fever. That would be things like endotoxin. Endotoxin is exogenous. It comes from outside of our body, but it's endo to the bacteria, right? So lipopolysaccharide or endotoxin, if our body sees that, it will automatically start a fever. We don't need signals from cells to tell us to do that. It just automatically starts your body to have a fever. So exogenous, this would be products made by the pathogens. Endogenous, these are signals sent by our cells to start a fever.
And endotoxin is an exogenous.
Mm-hmm. Yeah. So what is the point of fever? Finally, I'm sure you guys have just been waiting with bated breath to learn why we have fevers. So fevers, the high temperature can actually inhibit the growth of many organisms. Their temperature growth range is actually pretty sensitive. And so going outside of what is considered like body temperature, which is 37 degrees Celsius or 98.6 degrees Fahrenheit, that going outside of that range up to the 100, 101, 102, it's too hot for those bacteria to function. Your body is acclimated to live with that for a while. So that will inhibit the growth of many of the pathogens, as well as increase the metabolism of your cells. So while the bacteria are being inhibited from growing, your cells are actually being activated to do more work. And so that heat, sort of like if we kind of know this, right? Well, heating up in a chemical reaction increases the reactions in general. And it's the same thing. We're trying to increase the reactions within our cells by heating up our body. So we'll slow down the bacterial processes, but speed up our processes. And that's how our body has adapted to use fever to its benefit. So we'll speed up hematopoiesis. That's basically controlling, making more of our white blood cells to fight the infection. We'll speed up phagocytosis, and we'll also start speeding up that adaptive immune response, our chapter 16 stuff. That can be sped up by having that increase in body temperature. And then we have that increased body temperature helps with the cells getting to the infection area as well. So all of that is actually benefits of the fever. So generally speaking, it's not always a good idea to try to take fever reducing agents if you're sick, because these things are happening for a reason in your immune system. If you have an illness and you're not in terrible discomfort and you have a fever, let the fever do its job. However, if you're getting into that high fever category, definitely go to the doctor. That's not a take care of at home situation. If you're getting into that 104, or if your fever's been going on for a very long time, more than like 3 days, then you probably need to be going to see a doctor about your fever, right? Obviously, if you have little kids that have any kind of a fever, then you should probably be consulting the doctor. But for adults, that's the general medical advice, is that maybe let your fever do its job. It's there for a reason. Your body's adapted to have the fever, and in animals in general, that's what its purpose is going to be. So this is moving into interferon. Interferon is a cytokine. Cytokines, again, just signaling molecules for cells. So it's a signaling molecule that if I get infected with a virus, if a cell gets infected with a virus, it's a signaling molecule that infected cell will send out to let its neighbors know that a viral infection is incoming to their neighbors. So like I said, this is that call where your house is getting invaded by a burglar and you couldn't prevent it. And you know you might be a goner and the things that you own in your house might be goners. But you can at least call your neighbor and say, get the shotgun out, Bill, be ready. And then Bill can be ready with his shotgun. In this case, the cell that's neighboring not have an actual shotgun, right? But it's got antiviral proteins and things like that it can start making before it sees the virus. So it can be prepared and more ready to stave off that viral infection. So that's what interferon is. Interferon interferes with the progress of the viral infection by signaling the neighbors that there's one incoming. We're going to talk about it in chapter 16, but what do you think happens? What do you think your body does if you have a viral infection? Remember, a viral infection, you have a virus inside of you using your cell's machinery and your resources to multiply itself within your cells. So what do you think your body's going to do about that? It's going to attack itself. So your body's going to kill its own cells. So what your body is going to end up doing, we'll talk about it next, is it's going to go out and find those virally infected cells and literally just kill them. We'll sacrifice the few to save the many. And that's what your body is going to do in an immune response. So you wonder why you feel like shit when you got the flu. Your body is literally killing its own cells, literally. And so that's how your body's going to get rid of these infections. It's actually extremely effective because it does it very specifically as well, but it has to be controlled. We're going to get into chapter 16. But this last part for chapter 15 is the complement system. The complement system, again, is a very generic, very general response as part of the innate response. And so complement proteins, it's like a whole set of proteins. It's about 50 blood proteins, and I'm not going to make you memorize them or anything like that. But these things just exist naturally in your bloodstream all the time. They're not anything that we have to like activate and wait on it to be expressed and then all this stuff. They just exist in your bloodstream all the time, and they're always there. And so they're very, very tame. It's sort of like setting off like a cascade reaction, sort of like a nuclear reactor. You know, guys ever learned about how like basically a nuclear reactor is like one atom will get like excited, and then its excited parts excite all the atoms near it. And it's just like this cascade reaction is like exponential. And that's sort of like how the complement cascade is going to work. One complement protein will get activated, that one will activate several, and then the several, each of those activate several, and it just ends up being this massive exponential response suddenly in response to very general markers. All right, so it's a sequential cascade reaction. The three ways that you can activate this cascade reaction is through the classical pathway, the lectin pathway, or the alternative pathway. So the classical pathway means that an antibody bound to something. And because an antibody bound to something, the complement protein changes and it causes the whole cascade to start. So this is triggered by antibody. The lectin pathway, this is if we have proteins that recognize certain sugars on bacteria, if that reaction happens, then that can trigger the complement pathway. So it's the lectin pathway. So lectins are proteins in your body that recognize bacterial sugars. If they recognize them, triggers the complement pathway. Okay. Then we have the alternative pathway. So this is essentially molecules in your bloodstream that can recognize microbe patterns like LPS. It's very similar to PAMPs, but PAMPs are recognized by cells. In this case, these are just proteins that kind of see PAMPs and then activate the complement pathway. There's no cells involved with it, all right? So the complement pathway, again, is just a series of proteins. So what are those proteins going to do once they're activated? Well, the first step is going to be initiation. If you bound the antibody, or if lectin bound to sugars on bacteria, or if something interacted with LPS or a repeating molecule. So those are the three pathways, right? So if that happens, we initiate. And so that essentially means activating one of the complement proteins that's going to lead to amplification and cascade, which is the next step. So once you've excited one molecule in your nuclear reaction, the excited parts activate everything else. So that's the cascade part. So we'll amplify and cascade once we've initialized. Then we have polymerization and membrane attack. And we're going to talk about what that means in a minute. Let's see. Oh, I don't have a picture, but I did. Okay, so basically what happens is all of these complement proteins come together and bind together, and each one of these circles is a complement protein. They'll come together and create these holes or pores on the surface of a bacteria. So this is your bacteria, and this is each complement protein. So we'll do complement protein. And then this whole thing is something that we call the membrane attack complex. So polymerization means we're bringing the complement proteins together. They're polymerizing, they're binding together to create the membrane attack complex. So this is literally just going to create a big old hole in the cell. We've kind of already talked about why that would be a problem, right? Because the whole reason we have membranes is to keep what's in and to keep what's out. So we're poking holes in these bacteria so that all what's inside can just come out and they'll leak out their contents, as well as allows our attack proteins and things like that to be able to get inside. Because usually this isn't the only thing that's going on in your body, but this has its part to play in the response. So this will allow us to break open lice, the bacteria or viruses or whatever we're targeting. So that's one thing that complement cascade does. So other things that it does, this is one thing, membrane attack complex, probably the biggest, most defining characteristic. The other thing that complement cascade does is just initiate inflammation. Imagine that you have come in contact in your blood to a bacteria or something. You can help drive that inflammatory response by leading to signaling molecules that can help your cells respond to everything. So this just feeds into the entire inflammatory response. And then there's one last thing, which is something called opsonization. And basically what opsonization is, some of these complement proteins, they might be making this membrane attack complex, but some of them will just be kind of sticking out on the surface of the cell. If they're not creating that membrane attack complex, whenever you have these guys sticking on the surface of the cell, it acts as a molecular handle. You guys know how capsules create that sticky coating that's hard to grab onto? Well, complement cascade, when it's initiated, some of those complement proteins stick to the capsule and make it a lot easier for our phagocytes to grab on. and that's called opsonization. So when we have molecules like complement protein, an antibody can actually serve the same purpose. These molecules are for your phagocytes to grab onto, so it's easier for them to eat up the bad guys and digest them. So that can help that process. So you can have a capsule all you want, but we've got ways to help out with that. So that's opsonization. Just a little video here. Hopefully this isn't too long. No. Oh, this is not the video.
Every living thing needs to fight off other living beings that want to feast on them. So as multicellular life evolved over billions of years, it came up with ways to defend itself. Today, humans have a sophisticated defense network.
I'm gonna be a little faster.
Defense cells and weapons factories.
We're gonna have to.
But one of the most important defenses of our body is largely.
Oh, we're gonna get to it today. We're just not gonna finish it today. Yeah.
It evolved over 700 million years ago and is an army of over 30 different proteins that work together in a complex and elegant dance to stop intruders. All in all, about 15 quintillion of them are saturating every fluid in your body right now. Guided by nothing but chemistry, these proteins are one of the most effective weapons we have against invaders. Many other parts of the immune system are just tools to activate the complement system. But it's also really dangerous. Imagine having trillions of little bombs inside your blood that could go off at any moment. So our cells use numerous mechanisms to prevent complement from accidentally attacking them. Okay, what exactly does it do, and what makes it so dangerous? Shell, the complement system does three things. It cripples enemies, it activates the immune system, and it rips holes in things until they die. But how? After all, these are mindless proteins randomly drifting around without will or direction. Well, this is actually part of the strategy. Complement proteins float around in a sort of passive mode. They do nothing until they get activated and change their shape. In the world of proteins, your shape determines what you can and cannot do, because shape determines what you can interact with and in what way. For example, in your passive shape, you might do nothing. In your active shape, however, you might, for example, change the shape of other proteins, activating them so they can activate others. Mechanisms like this one can start cascades that spread very quickly. Imagine the complement proteins as being like millions of matches very close together. Once one catches fire, it ignites the ones around it. They ignite more, and suddenly you have a big fire. To show the actual mechanisms of the complement system is a tad complicated and overwhelming, so we'll simplify here. Now, let's imagine you cut yourself and a bunch of bacteria enter the wound and make it into the surrounding tissue. Our complement attack begins with C3. C3 is the first match, the initial spark that will start our fire. And to do that, C3 needs to switch from passive to active. How this happens is complex, but let's just say it can happen randomly through other complement proteins that bind to enemies or through antibodies. All you really need to know is that C3 breaks into two smaller proteins, C3a and C3b, that are now activated. One of these parts, the C3b protein, is like a Seeker missile specialized in bacteria, fungi, and viruses. It has a fraction of a second to find a victim, or it will be neutralized by water molecules. If C3b does find the target, it anchors itself very tightly to its surface and doesn't let go. By doing so, the protein changes its shape again. In its new shape, it's now able to grab other proteins and start a small cascade, changing its shape multiple times, adding other complement proteins to itself. Finally, it transforms itself into a recruiting platform known as C3 convertase. This platform is an expert at activating more C3 proteins that start the whole cycle anew. An amplification loop begins. Soon, thousands of proteins cover the bacteria. For the bacteria, this is very bad. It can cripple bacteria and make them helpless or slow them down. Imagine being covered by thousands of flies. But there's more. Do you remember the other part of C3, the C3a protein? C3a is like a distress beacon. Thousands of them flood away from the site of battle, screaming for attention. Passive immune cells notice the C3a proteins and awaken from their slumber to follow the protein tracks to the site of infection. The more alarm proteins they encounter, the more aggressive they get. This way, complement guides reinforcements exactly to the place where they're needed the most. So far, the complement has slowed down the invaders and called for help. Now, it's beginning to actively help to kill the enemy. The first immune cells to arrive at the battlefield are phagocytes, which means cells that swallow you whole, trap you in a tiny prison, and then kill you with acid. But to swallow an enemy, they need to grab it first, which is not easy because bacteria prefer not to be grabbed and are sort of slippery. But now the complement that has anchored itself to bacteria acts as a sort of glue that makes it easy for the immune cells to catch their victims. But it gets even better. Imagine being covered in flies again. Now, imagine them turning into wasps. Another cascade is about to begin. On the surface of the bacteria, the C3 recruitment platform changes its shape again and begins to recruit new proteins. Together, they begin the construction of a bigger structure, a membrane attack complex. Piece by piece, new proteins, shaped like long spears, anchor themselves deep into the bacteria's membranes, until they rip a hole into them that can't be closed again. Fluids rush into the bacteria, and their insides spin out. They bleed to death. The remaining bacteria are maimed and distracted by the complement and quickly taken care of by the arriving immune cells. The invasion has been nipped in the bud before it had the opportunity to become dangerous. You probably didn't even notice it. But while bacteria are not happy about complement, the enemies it might be the most useful against are actually viruses. Viruses have one problem. They need to travel from cell to cell. Outside of cells, they're basically hoping to randomly bump against a cell to infect by pure chance. Here, they're completely defenseless. And here, complement is able to intercept and cripple them so they become harmless and guide the immune system to devour them. Without complement, virus infections would be a lot more deadly. But wait, if we have such an effective weapon, why do we ever get sick? The problem is that in a war, both sides adapt. For example, when the vaccinia virus infects a cell, it forces it to produce a protein that shuts complement activation down. This way, the virus creates safe zones around the cells it infects. When it kills them and tries to infect more, it has a higher chance of being successful. Or some bacteria, for example, can grab certain molecules from the blood that keep the complement system calm and make themselves invisible. So the complement system, while being extremely important, is only one player in the complex and beautiful organization that is our immune system. A beautiful example of how many mindless things can do smart things together.
Cool. All righty.
Every living being needs to.
Yeah. All right. All righty. So we're at our questions. We're going to do the questions really quick before we move on. Question 1 is for Levi. What is a PAMP? Perfect. Oh yeah, that's fine. Yes. So, I mean, so examples of that, which I imagine you're going to do, but would be things like obvious, just general markers of bad guy stuff. Things like endotoxin, which is LPS, lipopolysaccharide, peptidoglycan, or double-stranded RNA. So our second question is for Jessica. How is lymph, I can't speak right now, lymph pumped through the body? Yeah, yes, exactly. Skeletal muscle movement. All right, third question is for me. Yes. What type of a leukocyte is a neutrophil? It's a granulocyte. All right, fourth question for Danny. What does dolor refer to? Yeah, pain. Yeah, we had that in the Kahoot, so luckily that was a primer for that one. And then endotoxin. Is it endogenous or exogenous pyrogen in our response? This one was for Jack, and I think Jack. Yeah.
Isn't it exogenous?
Yes, so that one is exogenous. So endotoxin, even though it's endo in part of the bacteria, it's exogenous for us and can serve as to immediately trigger our fevers. So it's pyrogen. All right, so we're going to get started on chapter 16. Real cool stuff. These are going to be our bombers, our tanks, or our tactical specialists, probably tactical specialists, but the better way for our T's. All right, so moving in, yes, question.
I was gonna say for the complement system, at what steps does it surround it and what steps does it like puncture it?
So it kind of does all of it all at once. Okay, so you'll have all of that kind of happening generally. So you'll have one part when you activate that C3 protein. I won't test you guys on C3, right? You don't have to know that necessarily. But when you do activate that C3 and it turns into the A part and the B part, then one of them will start triggering these pathways, and then the B part will start triggering the other pathway, but both of them are happening all at the same time. Like all the inflammatory response calling in the phagocytes happens at the same time. We start building membrane attack complexes at the same time as helping with opsonization and everything like that. So helping phagocytes eat guys up, eat the bad guys up. So all that kind of happens at the same time. It's just easier to kind of visualize it in kind of separate fashions. And generally, once a bacteria gets targeted by one side of it, that side of it sticks with it. But other bacteria, we don't usually get invaded by one bacteria, right? So it's the other ones might be having the other things going on with it. All right, so moving on to our adaptive response. Our innate response essentially is always going to be leading into this one, but it's a matter of how well your innate response is managing things that kind of dictates how serious your adaptive response is going to be. So this is acquired immunity, and it comes from your B and T lymphocytes. And this is essentially going to be governing your memory response. And it's going to create a very specific response to that specific pathogen. In fact, so specific that whenever you create an immune response to a specific flu, let's say H5N1 or something, you get a vaccine against H5N1. If it has any slight changes to it, suddenly your memory cells haven't seen it before. It looks completely different to it. So even the slight little changes in those proteins can need to institute a whole entire new response, which is why we need flu vaccines every year. It's for different strains because different strains are constantly coming out. And then they just might as well be a whole entire new virus to your body. All right. So all of this relies on immunocompetence, which is the ability to react with foreign things. And in fact, we have such a repertoire of ability to react to so many different things that we could technically react to 8.5 billion different antigens in each of our bodies. It's pretty crazy. This all relies on specificity. Like I said, in the adaptive immune response, we are reacting to a very specific antigen. That could be even a specific marker on a bacteria. So you might have cells that recognize the spike protein, the H protein of flu, and then you'll have cells that recognize the N on the flu. And that could all be happening in one single infection. And so you can react to several different markers on a pathogen, and each of those cells is only going to be recognizing that specific marker on that pathogen. It's a very specific response to a specific antigen. And it can lead to memory. Essentially, once we've seen this thing, we can have guys in waiting to see that thing again that can respond immediately without having to trigger this whole thing. As it turns out, your adaptive immune response can take a while to get started. It can take anywhere from 1 to 3 weeks to build up an appropriate response to something. Which is why when you get sick with the flu, it takes you a week to get over it, right? Start feeling better. This waiting on all of this to kick in. Your innate response starts doing work immediately, which is why you start having fever and why that fever lasts for days, because we are literally just waiting on your adaptive immune response. And once that adaptive immune response kicks in, the show's over. Like you won. So that's pretty much how that will work out if you can get to this point. So we already learned about antigens. Antigens are basically any markers that your immune system can see as foreign. So you can have an antigen that can exist that doesn't provoke an immune response. And you can have antigens that elicit too strong of a response. And we want to be able to see antigens or markers that are on your cells as self, right? So we have to train our body to not react to certain things as well. So all of this has to be controlled by our adaptive immune response. Because we can react to pretty much anything in the universe, you better be sure you're not reacting to self markers, right? So we've got to train our immune system with that. Geez. Yes, okay. So antigens, in order to perceive them as foreign, we can usually recognize the whole microbe or its parts, or we can have substances that are not even on a microbe. Could be chemicals, toxins, things like that, that are just like proteins floating around, or whole sugars floating around. It could be proteins, it can be sugars, it can be part of a microbe. It can be all sorts of, pretty much any molecule that can have a shape can be seen as an antigen. It doesn't have to be on a cell or on a virus. It can be just by itself. All right, so some guys are better antigens than others. And so what does our body react to the best? Things with complex shapes, usually we react to the best. Bigger things in general, we react to the best. Super tiny things or things that have repeating units, like it shows down there in the bottom, just a repeating unit of something, it's kind of hard for our body to have specific reactions to that stuff. That doesn't mean we can't, it just means it's usually a weaker response. So good antigens, it's usually based on their chemical composition, their size, basically what types of signaling molecules get activated by their presence, and all that sort of stuff. All right, so an epitope is the part of the antigen that your immune cells are going to react with. So when you make antibodies to an antigen, that antibody actually only binds to part of it. It's like saying, if I have this remote control, my antibody might recognize this end of it. This might be the whole antigen, but if I only bind with this specific end of it, that part of the antigen is called the epitope. So the epitope is the specific part of the antigen that's getting reacted to. So you might say COVID spike protein. So if this is a COVID spike protein, but we're only reacting with the very, very tippy tip of it, that's the epitope, right? A hapten, that's a term that refers to antigens that are too small to elicit an immune response by themselves. So they usually have to be paired with a carrier molecule in order to elicit a response. This is true of things that you already have knowledge of. Things like tetanus toxin. Tetanus toxin is a hapten. It's too small for your body to react to. So we pair it with other things in your vaccine in order to elicit appropriate response. So then when we have, this might be too small for your body to react to, but when I put tetanus toxin with diphtheria toxin or pertussis toxin, or all three, which is what you see in a Tdap vaccine, right? It's tetanus, diphtheria, and pertussis all at once. So we lump them together, and certainly you'll get an antibody that recognizes the tetanus portion while you're eliciting your whole response. We need a bigger thing to start the initial response, but once we have an antibody against this small thing, you might have pertussis and whatever else, diphtheria, attached to the tetanus. But once you've reacted to the whole thing, you might have an antibody that just recognizes just that. So when you see just that in the future, you will already have had a response made to it. Yes.
Tetanus is the one where, like, rust.
Yes.
Okay,
Yeah.
just wanted to make sure.
We usually think of rusty nails, and it's not rust that's causing the disease, right? But it just creates an environment that can harbor that type of bacteria. Yeah. So haptens are too small to elicit the response by themselves, but we can pair them with carrier molecules to help elicit that response. So that's the idea of this here. If we put just tetanus toxin into somebody, it will have no antibody made, but if we pair it to something else, a carrier of some kind, now you can have antibodies that will react to it. And then later on, they won't need to see it paired to something else. It'll already be able to interact with that epitope. An alloantigen is a term that refers to any molecule within a person that could be antigenic to another. So basically, like if I have A blood, right? And so if you give me B blood in my body will see that as foreign. But it's still a person molecule, right? It's not something that's coming from a virus or a bacteria or something. But my body could react to it. That's an alloantigen. Markers in other people that my body could see as foreign that aren't associated with a pathogen, but that my body could still see as foreign and attack it. It's why we need to make sure that we match up people for kidney transplants and things like that. Because alloantigens could be seen as foreign by the recipient and then they would attack it. Okay, so those are alloantigens. This is the most obvious one is going to be with blood transfusion and organ transplants. All right, super antigen is essentially, did you have a question? Or just, okay, you're fine. I just want to be sure. You're fine. Super antigen is any antigen that has a really strong cytokine response. So we have a lot of signals coming in and say, fight, fight, fight. Oh my God, we're getting attacked. Fight, 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 fight. But there might just be a small amount of a bad guy there. So it really creates this illusion of we need to fight this big, big, big fight whenever this problem isn't serious. We already know, because we learned in the last chapter, that that inflammatory response, if it's signaled too heavily, can cause damage to tissue nearby. And so you can have an overwhelming response trying to fight what you think is a big, big bad, but it's actually just a little problem. And that can cause damage in the body and can even lead to death in some cases, which is what we see in the case of cytokine storm, if you've ever heard of that. A cytokine storm is when we have too much signal for health. And then that can lead to shock and even death as a result. Your body thinks something extremely life-threatening is happening, but we've just got a minor infection going on, and it reacts big. And that's going to be a super antigen. An example of that are molecules that are associated with toxic shock syndrome. So ladies probably all know about toxic shock syndrome. You read about them on tampon boxes all the time. And if you have a situation like that, they tell you don't leave the tampon in for beyond this much time. And if you have a fever at all, you need to go to the ER immediately. You can die of toxic shock syndrome within a couple hours. So don't mess around with it. If you at all start having any symptoms of shock and you've been using tampons, you go to the ER. Now, a lot of the treatments of tampons nowadays have very, very well contained this risk, and it shouldn't be too much of an issue, but don't be leaving in tampons for 8 hours and taking that risk if you don't have to. Okay, that's all I'm saying. Because it can be life-threatening within a matter of hours, and it does happen still today. All right, so moving on. Antigen processing and presentation. In order to get our adaptive response going, you have to be able to trigger it. Now, this stuff is going to be killing your own cells. We're going to be creating antibody to fight something foreign. You don't want to trigger the bombers or the tanks to come in and start their big fights and their big war against probably maybe even your own cells if it's not warranted. So all of this stuff is extremely regulated. And so we have to wait for the right signals to come in the right order and with the right co-signals to regulate activating these guys. And all of this stuff starts out with your macrophages, your B cells, and your dendritic cells, your antigen presenting cells. So these are the only cells that are able to present antigen and start this response. So macrophages and dendritic cells, we've already learned, they are derived from monocytes and moved out of the bloodstream and into the tissues. These guys pick up whatever waste was left by the neutrophils and then go around and show it around in those lymph nodes to other cells and see if anybody recognizes it. B cells can do this as well, but B cells live in your lymph nodes. So B cells are just waiting in your lymph nodes for crap to pass through from your lymph. You stubbed your toe, you broke the skin open, bacteria got in, it gets brought in either from macrophages or just from the lymph. Let's say it's flowing in from the lymph, you've got bacteria and they meet a lymph node. And in that lymph node, we've got a B cell. And that B cell is like, hey, wait, I know you. I've been waiting literally my whole life just for you. Because your B cell, each B cell only recognizes one antigen. And that's it. It recognizes one antigen. For every antigen that your body can respond to, there is a B cell back there somewhere waiting for that one antigen. So that antigen has to find that B cell, but it will at some point. So it's waiting. You get a part of your bacteria floating around this pen cap, and that B cell's just waiting. And it's like, let me see your papers. And it looks, it's like, I've been waiting. I've been waiting for you. And so it will take that, and it can't do anything yet because it's a bomber, and that bomber can't just start releasing bombs just willy-nilly. First, it has to get the okay from its captain. I want to talk about the captain in a minute. Yes.
So the B cell is only in the lymph. So that bacteria has got to travel through your skin, into your blood, all the way to the lymph to find that B cell before the B cell can be active.
So that's one way it can get there. So the bacteria can either travel through the lymph and get to that lymph node, which could be, keep in mind, you don't just have lymph nodes in your groin and in here, you have them all throughout your entire body. But it has to find that right B cell, right? So either that bacteria got there through the lymph, or your macrophages that went to go clean up the mess from the neutrophils, they can carry the part with them. So it can take the parts of the bacteria where you stubbed your toe, the macrophages are cleaning up that mess, and they will take those parts to the lymph nodes and literally just keep looking around to see if anybody recognizes it. So it can either, the thing travels there on its own, or it can be brought there by the macrophages or dendritic cells. Make sense? Yes.
So basically, antigen cells are just like, hey, we made antigen for this.
Yes, yes. So antigen presenting cells, which could be B cells, or it could be the macrophages or dendritic cells, they have picked up some foreign matter, either by cleaning up at the site or by it passing through the lymph. They've picked up this foreign thing and they're being like, hey, help. I found this thing. So macrophages are literally being like, I found this general thing. Does anybody recognize it? The B cells are saying, I found the thing I see that I was made to see specifically. Let me go fight. But it has to get the okay from the captain first. So we'll go through those two possible scenarios, either the B cell finding the specific thing, or the macrophages just being like, hey, I found some crap. Anybody know what this is? So we'll get to that in a minute, all right? But those are antigen presenting cells. Based on how you come into contact with an antigen dictates basically what kind of response you're going to have, all right? So antigen presenting cells are APCs. Those antigen presenting cells, they pick stuff up from outside the cell. And that makes sense, right? We've been talking about macrophages going and cleaning up crap they found outside. Or we find stuff floating outside in the lymph, and the B cell picking it up and recognizing it. So stuff that was outside. What happens though, if your body already has the virus inside of a cell? All right, so if you're an antigen presenting cell, B cell or macrophages, antigen presenting cells, those are the only ones, macrophages or dendritic cells, same thing, honestly. But, or you're a B cell, and you picked up something from outside, then you're gonna hold it onto it. You're gonna have ingested it usually by either your B cell, you got the specific signal saying, I recognize this thing, and so you are gonna react to it that way. Or if you're a macrophage or a dendritic cell, you phagocytosed it. Okay, just because it was a foreign thing that you ate up, and now you're gonna be like, who is this? What is this? Anyway, so antigen presenting cells, no matter how they got it, if it came from outside of the cell, they're gonna wave their flag on a molecule called MHC2. Okay? MHC2 is what we use to wave our flag for stuff that came from outside of the cell. Bacterial infections, for example, often happen outside of our cells. But what happens if a cell is infected inside with something? Then what if our outside guys never saw it? Sure, if you have a viral infection, there's going to be some virus outside of the cell. But what about the ones that are inside the cell? How do your infected cells call for help? As it turns out, if you are infected, every single nucleated cell in your body, if it has a nucleus, it can get infected with the virus. Because viruses use that machinery, right? So they have something called MHC1. And what they'll do is if they find foreign stuff inside of the cell, they'll wave that help me flag with that molecule that they found inside on MHC1. All cells can do that. So that's for viral infections, for infections that are inside the cell. And that's actually how I remember which one does which. Because to me, MHC1, that looks like an I for inside. If it came from inside, we'll wave it on MHC1. And any cell needs to be able to do that because any cell that has a nucleus can get infected and therefore needs to be able to call for help if it does. All right, MHC2, or sometimes you'll see it written as Roman numeral 2. This one looks more like an I to me. The 2 is stuff that came from outside, and it's only dealt with by antigen-presenting cells. Only antigen-presenting cells can pick up stuff from outside and present it on MHC2. So only antigen-presenting cells have MHC2. All of these MHC markers it's called the major histocompatibility complex. Also, yes, you do need to know that. All right, so the major histocompatibility complex. It's also known as the human leukocyte antigen, or HLA. When I talk about how I worked at a transplant lab, our lab was actually specifically called the HLA lab. Because what we did was we looked for those MHC1 markers. They're just a general molecule that picks up stuff from inside and presents it. It's not antigen specific. It just, if anything from inside, it can present it. But it helps your cells also recognize that it's self-presenting that stuff. And so my cells, my T cells, can come and recognize that MHC1 is a self-cell, MHC1, presenting something from inside. Your MHC1 molecules look different than mine. All of my cells have MHC1, right? Any nucleus cell, any cell with a nucleus has MHC1 and can signal for an infection inside. Your cells all have your MHC1, and my cells all have my MHC1, and they can differ slightly just from genetic variants. And that signal of saying self is calling for help, when my cells see your cells just having MHC1, not presenting anything, but just having it, it sees your MHC1 as foreign and automatically attacks it, unless your MHC1 looks like mine, which is why the genetic testing for organ donation is so specific. Your MHC1 has to look exactly like my MHC1 in order for me to receive your kidney. Yes.
Do identical twins have the same exact
Yes. Yes.
but not fraternal?
No. But they could potentially have similar ones, right? But we would have to check that, but there's no guarantee, right? So anyways, that is the gist of what MHC is. So its actual function in the cell is just as a flag holder. It's just a flag holder. Flag holder. It's waving the flag saying, I've got something inside me. That's it. And the flag might have a specific antigen on it, but it can hold any antigen that came from inside. All right. And that's all it's doing. So if I'm an infected cell and I'm like, oh my God, I've got a virus in me. What is this? Help, help. I've got this. What is this? Help, I need help. That's MHC1. Okay. If I'm a macrophage, I'm coming up and cleaning up and I find this, I'm like, oh, neutrophils left this crap around here. I'm going to take this to the lymph node and be like, anybody know what this is? And I'll look for the cells that can help me with. So that's going to bring us into our next set of cells, which are going to be our captains, because none of the next step can proceed without the captain. Okay. All right, we're gonna stop there. Yes, we did class 1, class 2, right. So we're gonna come back to this slide, slide 15, when we get back next time, and we're gonna go up to the lab now. Anybody have any questions on any of this stuff so far?
Are we doing actual lab there? Or are we doing the one project? Are we-
We're gonna update our unknown lab, and we're gonna do a Grams thing.
Okay. Cause I was like, the upload of lab is.
Yeah, it's nice. I have nothing too much pressure here today. It's the first day back from spring break. I didn't want it to be overwhelming. All right, so we have slide. I better mark it down or something.
I have my little place, you know, if you want one.
Thank you. I can get my pen out. Today is the 24th.